Good evening, everyone. My name is Jyoti Sharma, and I will be taking this 2 hour class for week 10. So, the course name is Environmental Quality Monitoring and Analysis, and the live session will be from 6 to 8 p.m. This is my brief introduction that right now I'm a PhD student. I did my master's from FRI Dehradun, and my undergraduation was from University of Delhi. I have cleared UGC NET GRF and ICR NET also. And right now I'm a PMRF research fellow, and that's why I have this teaching responsibility of taking 2 hour class every week. I already have some NPTEL experience. For example, I already have taken the live session for air monitoring and control, environmental chemistry and microbiology, basic environment engineering and pollution abatement. So I think this will help me to run this course in a smooth manner also. This is how I teach. So I have multiple choice question, a lot of multiple choice question I have, and then uh, I throw this question to the audience, and audience reply. Write in the chat box whatever the wrong or right answer that audience is considering, because and then I give them the correct answer. So please don't worry if you are thinking that there may be this answer or not, but I think your participation is highly valued. If you will speak, then I can discuss about that question more, and there that will bring more clarity about that particular topic. So yeah, I will encourage you people to participate. Okay, so I think I will take 5 to 10 minutes to recap what we have learned, because right now we are talking about week 10, but we already have covered from week 1 to week 9. So I just want to give you the brief what we already have understand, and at what place we are right now. So we started with very basic introduction of this environment monitoring and analysis, where we talked about the compartment of the environment. So compartment of environment, maybe air, maybe water, maybe soil. So we talked about compartment because these compartment are important, because our pollutant or contaminant are present in this compartment only, and that pollutant may move from one compartment to the another. So we talked about some chemical, and then how it can move from one particular compartment to the another compartment. Then we talked about what different parameters we have to test whether our air quality and water quality is uh, good or not. So for example, for air quality we talked about BOD, COD, theoretical oxygen demand, and a lot. For air quality parameter we talked about the concentration of carbon dioxide, ozone, and pan. So we talked about these, and we particularly talked about particulate matter also. So this is how we started our week 1. Then in week 2, because as I told you, the contaminant or pollutant may move from one compartment to the another compartment, but this is not the random movement. This movement is governed by partition constant. So for example, if we have a movement of any pollutant or contaminant, air to water or water to air, then we will talk about this Henry constant. Then there are some constant that we can generate ourselves, for example soil to air, air to soil, and likewise how we may have different phase, and uh, the contaminant will move from one phase to the another phase. So based on that we can calculate the partition coefficient, and based on that value of the partition coefficient you can tell, okay, so where my most of the contaminant will be staying. Okay, so that's why. And like from week 2 to week 10 we are continuously speaking about this soil air partition coefficient. So I think this is again important for us. uh, Then in week we started with introduction to environment monitoring, and simply as I told you, we talked about a lot about the environmental compartment and the pollutant that we have in that compartment. So uh, but to measure that, to analyze that particular contaminant is also important, and for that we started with the quality control. So we talked about the precision, we talked about the accuracy of any type of analysis what we will do. So we talked about such kind of terminology, so that whenever we are doing any kind of analysis, that analysis should have some valid results, right? So this was covered in week 3. In week 4, we, as I told you, we have a lot of contaminant, and contaminant will move from one compartment to the another compartment. So in week 4 we took the example of the organics. So as my default always my default example is benzene. So if, and we know that benzene have some carcinogenic effect, so that can cause the cancer. So if benzene, if we are moving this benzene from air to water, the first thing is how we can calculate the concentration of this. The second thing is, can this benzene move from air to water, and what is the partition coefficient for that? So we talked about how we can absorb organic from air to water using a lot of solvent, and we talked about a lot about, if we have contaminant that is organic in nature, the solvent should be organic in nature only. So we talked about these in week 4. Then week 5, we extended this analysis of organic load only in water. Uh, and then for this analysis part, so in week 4, we started with how we can absorb uh, organic load in the water. But in week 5, if we already have absorbed organic load in the water, then how we can analyze this? So we can analyze this using chromatography and mass spectrometry. Chromatography will separate your different interest of chemical, and after that mass spectrometry can give you idea about what that contaminant or chemical species it may be. So we talked about this in week 5. Then in week 6 we started with monitoring method for air and vapor, because we have like, in brief, if I say, we have two way by which we can measure any gaseous component that we have in the air, either directly. So this is something, grab air sampling, if you have heard, grab air sampling, and then we will give it to mass spectrometry and chromatography like this. The another, maybe we can absorb it first into some liquid, we can concentrate it, and then we can let it to go to the mass spectrometry. So we talked about this, and little bit about measurement of the microorganism. This was very brief, but yeah, we discussed about this also. Then we started to see how we can use uh, chemical engineering part to model how our air pollutant is moving from one place to the another place. So, and even if we have river, and if we are dumping some pollutant at some place, then can we monitor this, can we track this, what concentration we have at each distance the river is flowing, so in the downstream. So we try to calculate the concentration at some distance. So we were able to do this by box model. So using even right now we will use about this box model, because the concept is very clear. We should have mass, and the rate of mass that is entering or entering or going, or there is a reaction. So the mass rate should be conserved. So this is the crux of your box model. Then we talked about, if we have different meteorological condition, if we do have different wind condition, or radiation or cloudy condition if we will have, then what will be the stability of your atmosphere, the first thing. The second thing is, based on that stability, how your pollutant will behave. Your pollutant will come to the ground or will go on and will spread and will do the dispersion. So this is depend on your lapse rate, mixing height, and meteorological parameters. We talked about this. Then we moved from this water to the air, and this was the dispersion model. As again, we already have discussed this in week 8. I'm just giving you the recap. So this is something, like each plume is following the normal distribution. So normal distribution means at the center line you will have the maximum concentration, and there will be spread at the tail, and where we will have a less concentration. And based on this Gaussian dispersion model, we can estimate the concentration at x, y, and z direction, right? So or you can say x, y, or z dimension. So whenever we are required at what place, if we want to measure any concentration, then we can measure. So what we are doing is we are utilizing the physics, the uh, chemistry, and some concept of science, so that we can have the model to track the pollutant, either it is in air or it is in water. So we are doing like that only. Then in week 9, week 10 is the extension of week 9 only. So in week 9 we started with the interface mass transfer. So this is important, like from the week 1 only, the pollutant will move from one environmental compartment to the another environmental compartment. So the thing is to move this between different environmental compartment, there may be some resistance, there may be some diffusion, based on what chemical we have, what different phases we are talking about. So based on that, we need to learn about the diffusion, if it is interface mass transfer, the first thing. The second thing is the overall mass transfer, because uh, there is a thin layer that can create the resistance. Uh, Deepa, can you please mute yourself, or should I? Yeah, thank you. Thank you so much. So we started with uh, this interface mass transfer, and we will extend this in week 10. Yeah, so in week 10 we will take some example, and we will try to simplify this interface mass transfer. So yeah, this is the brief, that what we already have understood and what we are gonna um, understand or learn in this week, right? So again, I have MCQ questions, so you people are encouraged to write in the chat box whatever answer you are thinking, right or wrong. Okay, why interface concentration are unknown, and I have four options. They are constant, too large to measure. Interface thickness is molecular scale. Diffusion is zero. Don't worry if you do not know what is this interface. Then I will explain this also. So interface concentration are mostly unknown. Why? Okay, so let me tell you that, for example, we have two environmental compartment. So let me take this pen. Okay, so let's say we have here gas, and here we have liquid. And if there is any contaminant A, so let's say if I have contaminant A or pollutant A, that can transfer to the liquid phase. But there is the interface. So interface is the line that is separating different phase. Okay, so interface is the line that is separating two different phases. So this line is known as interface, right? Then uh, okay, let me take another color. So for the gas part, the interface length may be something, and for liquid part the interface length may be something. So this is the length of the interface, or you can say the thickness of the interface in the gas side, and this is your thickness of interface in the liquid side. Okay, but this size is in the molecular scale. So that's why, yeah, B, C answer is the right one, because this thickness is just the molecular scale, and at this, because the thickness is just the molecular scale, then how we can calculate the concentration at the interface? So this is very difficult for us. If we are able to calculate this concentration at the interface, it is very easy for us to calculate the resistance that we may have if our pollutant is moving from one compartment to the another compartment. Because this interface concentration calculation is very difficult for us, that's why we have to simplify it with some concept. And the reason only that this interface concentration is unknown is that because our thickness is at the molecular scale, and that's why uh, it is very difficult for us to calculate this interface concentration. So yeah, C answer is the right one. Okay, I'm giving you one equation, and that equation is Na is equal to small k. In bracket, we have Ca2 minus Ca1. So why can't we write this equation? Unit mismatch, phase differ, diffusion invalid, velocity unknown. So most of the time, what we do is, let me again do this. So let's say this is the interface, and this is my interface thickness, and this is my gas. So and so gas. So let's say this is an A1 because this is gas. K, and this is C. What we have to do is, if our anything is moving from liquid to gas, if anything is moving from liquid to gas, then what we have to do, we have to write is, because this is the interface in the gas side. Okay, so this we can write, this may be equilibrium, and there is always equilibrium in the gas side interface and the liquid side interface. So that's how. So this is your equilibrium at the interface, minus, and this is 1, and this is C again, 1, and A. Yeah, we write in such a way. We write, what we write is, we write K, and in bracket the concentration is in the gaseous side, but what we are doing, we are subtracting the interface concentration. We are subtracting our gaseous concentration of pollutant A from the concentration of A in the interface. So what I can see is, we are taking this 1 1, we are not changing the phase. Can you see the phase is same, 1 1? This is gas gas. So in this equation, but what equation that I have given you here, it is A2 and A1. We can't do this. Why? Very simple. If we have pollutant uh, and if we are subtracting it, it should be in the same phase. If it is an if it is in gas, then this should be in the gaseous phase only. If it is in a liquid, then it should both these terms should be in the same phase so that we can compare it. But if we have a2 and a1, then this is not the right thing that we can have. So B answer is the right one. So in the next question, what you will see in such kind of equation is that here the concentration we are subtracting, right? So let me again, in a different way, let me clarify this. uh, so what we have learned is, if we want to create any gradient, so that gradient is created when there is a difference in your concentration with some distance, right, in some thickness. Okay, and this difference in the concentration, there will always be the difference in concentration in different phase. Okay, but because we are talking about the interface, so we are more worried about this interface and moving to the gas, let's say. So this is also the gaseous phase, but the this is also the gas phase, but this is interphase, right? And this is not the interface, but this is the gaseous phase. So we have to compare these two to create the gradient. So the phase should be similar. So that's why we can't directly write equation like this. I think I'm able to make you understand, but I don't know. Anyway, so B answer is the right one. Okay, the next question very important because this week 9 and week 10 is related to these kind of equations only, and this equation says that 1 by capital K, just see this is capital K, so 1 by capital K is equal to 1 by small k2 plus 1 by h small k1. So what does it imply? Parallel resistance, series resistance, no resistance, only one phase matters. Uh, in parallel, no, this is not parallel resistance. This is something else. Can you guess something else? This is not parallel. Yeah, actually B is the right answer. This is the series. So if you have heard about your resistance in 1 by r in the physics, uh, if we have resistance in the series, then this is 1 by r is equal to 1 by r1 plus 1 by r2. We have learned this in 8th or ninth standard, right? So if we have resistance in the series, then the sum of resistance would be look like this. So that's why, so let me tell you why we are talking about the resistance. So again I'm drawing this boundary. So this is again gas, and this is again your liquid phase, and we have some uh, interface. So this is so we have a very thin layer of interface in the gas side, and we also have interface thickness at the liquid side. Okay, so it means if a chemical A will move either in direction, or if the chemical A will move in this direction, there will be some resistance due to these interface in the gas side and in the liquid side. There always be some resistance, but how much resistance it will give is so this K2 is the resistance. So this is something that you can mm, this is something like that. If you are moving your contaminant from air to water, so 2 is water and A is air, 1 is air. So if your contaminant A is moving from air to so this one, air to liquid, so this will be your small k A2 and this one. So this resistance will be uh, this resistance the sum okay, let me tell tell you again. Okay, so the resistance that we will have is the sum of the resistance that we have in the gaseous side and the liquid side. So this is not the small, but I can say this is the capital K, capital K2. So this is something, this one. Okay, so this is Ka2. I can write it fully. So this is Ka2. This is the resistance due to gaseous phase, gaseous interface and the liquid interface. But this is the sum of uh, the resistance that is due to your liquid and due to your gaseous interface, and with the Henry constant. Okay, so what we have learned is that if we are moving any contaminant from one phase to the another phase, there will be some resistance. The overall resistance will be your K, capital K. Overall resistance will be your capital K, but this resistance is due to the interface in the air and the interface at the water side or the liquid side. So this is small k1 and this is small k2. And if we are adding them in the series type, then we will have the total resistance. Okay, so this is how we can calculate this. And yeah, it is related to the resistance just like the Ohm's law. So if we have different resistance, we can sum in the series. So this is the reciprocal. That's how we can add the resistance. I have a few numerical question on that also, but I think that will come later. Okay, so if your K1 is less than K2, then what will happen? Which side will control? Gas side control, liquid side control, both equal, no control. If your K2 is larger, what will happen? Larger than K1, small K1. So just don't confused with the value, but if it is the resistance, then it is 1 by K, right? 1 by K2, 1 by HK1. So if this K2 is larger, it means the resistance, because this is 1 by K2, right? Resistance will be very small, is it? Because I gave you, let's say K2 value is 50, but the resistance it will give me is 1 by 50. So this will be something 0.02 or something. Yeah. So it means whenever there is the value more, it means it will give me the less resistance. So what will control? This will control, right? This will control, and this is, one is for the gas, right? Is it? One is for the gas and two is for the water. So what should be the answer? Um, yeah, Lakshmi gave me A. Yeah. So A is the answer, because what we are doing is, at last, to calculate the resistance, we have to flip it. and whenever we will flip it, then this will give us the reverse result. So please keep this in your mind. Okay, again I have same equation of the resistance, and K1 is given, that is 0.01, K2 is also given 0.1, and H, that is the Henry constant, is 2. So you need to find the dominant resistance. Again, the same thing will apply. What side of resistance will be more? Yeah, A is the right answer. Again, let me give you. So this is 1 by K is equal to 1 by 0.1 plus 1 by, we have 2 into 0.01, right? So this is something 1 by K is equal to, if I'm keeping this point above, so this will be something 10 plus this will be 50, is it? So what will happen? So the resistance, which will dominate more? Gas side, is it K1? Yeah. So this is how I think you can calculate which one will dominate. So this is something like 10 plus 50, that will be 60, but 50 is more, right? So gaseous side will give you the more resistance. Okay, so if our system is well mixed, concentration profile is linear everywhere, flat in bulk plus steep near interface, zero everywhere, random. So this is something that if you have this liquid, we have gas here, and here we have liquid, and we have well mixed liquid here, right? We have well mixed liquid here. Then if I'm calculating this concentration profile, so will it be linear everywhere, flat in bulk and steep near interface, zero everywhere, and random? Yeah, B answer is the right one. That we have this flat in bulk. So this is something like, if you are having any sugar water in any container, so or let me take some benzene something so that it can evaporate in the air. So let's say I have benzene in the water and I have fully mixed. So this is well mixed, right? This is well mixed. And but what will happen is, no doubt benzene will evaporate if it is not closed. Okay. So, and what will happen at here at the interface? So this is your gas and this is your liquid. This interface thickness will be very low. So whenever you are steering and whenever you are well mixing the thing, it means your thickness, you can denote this thickness with delta. So your thickness will be very low. And if it is a very low, it means here we have steep gradient. very steep gradient because the thickness is very low. So it is something like dc upon dt, sorry, dz, or you can say delta, or you can say delta. So the concentration will rapidly change in a very small thickness. So it means there will be very steep at the interface. Okay. Even if you are well mixing, if there are two phases, there will always some resistance, and that resistance is due to there will always some interface thickness, right? And if we will have if we have well mixed system, it means your thickness will be very low, and that would create the steep concentration gradient, very steep concentration gradient. Okay. And if we our system is not well mixed, your thickness will be very higher, and the gradient will be like slowly it will decrease with the distance. Okay. So that's why b answer is the right one. Yeah. If we are increasing the steering, then it will increase the delta, it will decrease the delta, it will remove the interface, and it stops the diffusion. So we have this, uh, we already have learnt about this Fick's law, right? So what was the Fick's law? This is something that your flux, your flux is dependent on diffusion plus advection, right? Your the flux that will move from liquid to gas, something like that, your flux will depend on your diffusion and the advection. And in diffusion, what will art is minus d dc by dz. So this is the change in the concentration, and this is change in the distance. So this is something, you have liquid here, and this is your interface in the liquid side. So here, or here, like anywhere, this is just your interest, where you are taking your reference. So anywhere the z will be equal to 0, and here z will be equal to something z. Okay. So in this phase interface, or at this thin film, there will be the change in concentration. Here concentration will be normal concentration, but here concentration will be little less, right? With the distance, the concentration will be less. So this is something how the concentration is changing with the thickness, and with the diffusion coefficient. So that will give you the flux due to the diffusion. Okay, so here this dz, dz is what we are saying, it's the uh, delta. Okay, so if we are steering it well, so if we are steering the well the liquid, then what will happen? The thickness will reduce. This dz will approach to 0 but will never be 0. Okay, it can't be 0. So if there will be 0, then it means there will no there will no any resistance, but there is always some resistance, right? So there will always some thickness, but if we are steering, then we are reducing the thickness, and reducing the thickness means we are decreasing the delta. Yeah. So let me see. Yeah, Lakshmi gave me right answer. That is the B. Okay. So I already have explained, I think, in the next, in the previous slide only. Uh, can we have delta 0? Is it possible? Yes, infinite mixing. No, interface always resists. Only in gaseous, only in liquid. Delta, that is, this delta is nothing but this is dz. So this dz can be zero. Is it possible that we have dz that is equal to zero? If we are steering it well, infinite mixing we are doing, then uh, will this distance of your interface thin film, the difference will be zero or not? Yeah. So B is the right answer, because as I told you, even if you are mixing very well, so for example, you are mixing benzene in the water or benzene you have in the air, but it will move to the liquid phase, or it will move, or from air to it can move to the gaseous phase. And at that thin film that we have in between, that are separating these two phases, there will always be very this thin film. Okay, and this can't be zero. This can't be zero. And that's why interface will always be there, and that will resist. That will resist, and that's how we can calculate that resistivity whenever we are transferring this mass. So while calculating the mass transfer coefficient, the important thing that we have is the resistance at the interface. Okay, that always be that can't be zero. Okay, and that's why B answer is the right one. Yeah, so due to interfacial tension and the molecular effects that we have, this can't be zero. Okay, so we have mass transfer coefficient, that is small k, that has the unit of meter square per second, meter per second, kg per meter cube, mole. Mass transfer coefficient. So, what can be the unit? So you can calculate it using. So let me give you one equation. The equation is, we have flux, and we have, let's say, K2, and so we have, let's say, this one. This is the one flux that we can calculate, right? This is A2. So this is something that if we are moving from air to water. Oh, sorry, I gave the wrong. So here this will be this one, and here we will not have anything. This is something infinity or something, you can say. So from here, can you do you know the unit of flux? If you know the unit of flux, and if you know the unit of concentration, then this you can calculate very easily. Flux divided by concentration, that will give you the mass transfer coefficient. What is the unit of flux? Flux unit, and then the concentration. And if we are dividing it, then we are having the mass transfer coefficient. So mass transfer coefficient is mostly meter per second. And let me tell you what we have is, so yeah, so for the flux, here in place of mole you can also say kg or gram something. This is just the weight, so you can have any unit here, it will be cancel out. So flux is something that how much mass you have per time per area. We all always have learned this, right? In mass balance we talked about mass per unit time, but in the flux we have to take into consideration the area also, right? So the flux unit is mass per time multiplied by the area. So this is your flux. Then concentration, concentration is mass by volume, is it? So this will be kg per meter cube. So we are canceling out this one, this one. Here we have two. Keep it now one, and then we have the second. So this will come up and this will go down. So this will be meter per second. It means your mass transfer coefficient unit is mostly mass per second. Sorry, meter per second. Is there any doubt? Then you can ask me. Otherwise, I'm going to the next slide. So if we have gaseous phase that is highly turbulent and liquid is stagnant, you have to tell me the right statement. Gas resistance dominate, liquid resistance dominate, both negligible, no mass transfer. So this is something, you have gas that is highly turbulent. So there is some wind velocity that is moving, and that's how it is making a turbulent condition. And here the liquid is very stagnant. It is not moving. And if there is any contaminant that is moving from this side or this side, which side will give me more resistance? If we always learned that if we do have more velocity, what velocity is doing? Velocity is steering something, right? It is mixing something. If it is mixing something, then resistance will be very low, because that the thickness will be very less. We talked about this, right? If we are steering anything, or if we are mixing anything very well, it means it will reduce this dz, so your delta will be reduced. It means your resistance will be less. Or the another example that I can give you is, for example, there is a plume and you are moving the fan, or you are switch on the fan. What will happen? There will be huge diffusion, okay, huge dispersion that will happen. It means your molecule will move very fast and it will disperse. That means resistance has been reduced, is it? So if we are making anything turbulent, it means we are reducing the resistance. Okay, and that we also learned in stability, atmospheric stability also. So if our wind is stagnant, pollutant can't move from one place to the another place. Your atmosphere should be very unstable. There should be some velocity. There should be some wind flowing. That's how your pollutant can move from one place to the other place. If it is a moving, then it means the resistance is less. So it means if your gas phase is highly turbulent, that means it is giving me the less resistance. If your liquid is stagnant, then that will give the more resistance. So your liquid resistance will dominate. Just take the example of your what should I give you? uh, Yeah. So let's say in the gas we have benzene. Okay. And your air is flowing. So wind is flowing. So your benzene will move from one place to the another place, and that benzene will also want to move to the another phase, to the liquid. But if we have liquid very stagnant, then there will be a very clear uh, thin interface layer. Okay, that will create the more resistance. So by which what I can say is the B is the right answer, not A. So just keep in the mind, the crux is, if we have system unstable, if we are mixing everything, then your resistance will be less. So your thing can move from one place to the another place easily. If your system is stagnant, it is not moving, it means it will give you the resistance. Okay. Another example that I can give you to make you more explain, if if your trolley bag is moving, it is moving, right? Rolling friction, if you have heard about this. So if your trolley bag is moving, it will move. But if your trolley bag is stagnant, it is not moving, and then you will start to move it, then there will be more resistance to it. No doubt this is more example of inertia, but by which you can also learn, if the thing has been stopped, then this will create more resistance. So I think that's the explanation for a B answer to be the right one. Okay, now we are moving little ahead. So if you have pollutant A that enter a completely mixed tank by inflow, leave by outflow, and is removed by volatilization, there is no any reaction. So what is correct mass balance? Accumulation is equal to in minus out plus volatilization, in plus out minus volatilization, in minus out minus volatilization, in minus volatilization. I think very simple mass balance that I asked in this question. Yeah. So C answer is the right one. We already have learned. So for example, this is our lake. There may be some flow that can come. So by flow, there may be some coming in. By flow, there may be out. But without flow, with some diffusion or with some other processes, your things can go out. For example, volatilization, right? And if there is no any reaction, so there are no any processes that are going on. So these are out. This is also out. This is in. So in minus out, out by flow, and out by volatilization. So this will give me the accumulation rate. Right. So I think there is a no problem with this option. So yeah, C1 is the right one. Okay, we are moving little more ahead. If we have species A that diffuse in the positive Z direction, concentration decrease with increasing Z, which is true. dCA divided by dZ more than zero, flux is negative. If it is more if this is less than zero, flux is positive. It is less than zero, flux is negative. It is equal to zero, flux is positive. So this is something related to the Fick's law only. So for example, your Z is equal to 0. Initially, you didn't have any thickness. Okay. So we start with the when. So let's say this is your thickness. This is your thickness where z is equal to 0 and then z is equal to z, and that's how this is giving me um, dz, right? So what I'm saying is my concentration is decreasing. So let's say here my concentration was c, okay, and if I'm increasing the z, then my concentration is reducing. Okay, so which one, which is true? This is related to the Fick's law only. So we have, this is your Fick's law, right? For the diffusion. Yeah, B answer is the right one. Yeah. So this is something, and this is flux, right? So your flux due to diffusion is equal to minus d. D is diffusion coefficient, change in the gradient with change in the z. Okay, so if your concentration is reducing, if your concentration is reducing, what does it mean? That here I had more concentration. So let's say this is C1 and let's say this is C2. Uh, I can say, so C1 minus C2, and then here I had 0 minus, let's say this is Z. Okay, or we can flip this also, so that at the denominator I have the positive things. So this is C2 minus C1 Z. Okay, and that's how, because here the concentration is reducing, and yeah, I have to do the minus sign here, because the concentration is reducing. This minus sign and this minus sign, this will give me the positive. Right. It means when my concentration is reducing, that's how this is less than 0, my flux will be positive. Is it? Because this is, there will be two minus sign, and that's how we will have the positive sign. So I think the next, yeah. So this is something that because your concentration is decreasing with z, it means it will be less than 0. If this will be less than 0, then this will be, your flux will be more than 0. That means this will be the positive, right? Okay. Under steady state with constant diffusivity and no reaction in the film, the mass flux through a stagnant film of thickness delta is. So you need to tell me the mass flux. And mass flux, when we do have the steady state with constant diffusivity and there is no any reaction in the film. This is very much related to the Fick's law. This is just some rearrangement of the Fick's law. Just do the rearrangement of the Fick's law. What was the Fick's law? Minus d dc upon dz, right? And dz, what we can tell, this is the delta. So it means d upon delta dc. And this c we can expand because this is the difference in the concentration, right? So if this is the concentration difference, then yeah, B is the right answer. So let me see. So this will be, so this is the concentration difference. Okay, so concentration difference we have in this four options I have, but this one particular, I think this is very simple to see. So this condition is just given in this option, right? And this part we will learn, I think, in next few slide what it is. So yeah, B answer is the right one. Okay, for transfer across a stagnant film, the mass transfer coefficient is small k is equal to delta d, d by delta, delta by d, 1 by d delta. I think again from the Fick's law, very easy. So what we have learned is that uh, if we have any flux, if we have any flux or any movement, that movement is due to some driving force. That driving force is due to some difference, potential difference, divide by resistance, right? This is like Ohm's law, right? So I is equal to V upon R. Okay, so this is something like that. Okay, so this is, so you have flux, this is minus d dc by delta. Okay, what we can write it, dc, how we can write this, delta divide by d minus, right? So this will be your potential difference and this will be your resistance, is it? Yeah, so that's how C answer is the right one, or the opposite one. Let me show you here actually. So this is something, yeah, here what we are writing, so this is something that we are getting confused here, is that your flux is, here we are just writing this the small k, yeah, mass transfer coefficient, and we know that if we are expanding this, so this will be like this one, is it? And here k will be equal to d by delta, very simple. So yeah, without going to the Fick's law, or from here to here we are going, then I think this is giving us the right answer, not from this one to this one, right? So yeah, if there is any problem then you can let me know, otherwise we just need to flip the things, because here we have k, we have this k is not at at the bottom, but this is with your concentration, because this is right now the mass transfer coefficient. Okay, I think this will again help you to make you understand the previous question. If Na is equal to small k Ci minus Cb, then resistance per unit area is. Now this is because this is resistance. Okay, so again I'm saying dc upon dz, right? Or something like we have potential here and here we should have resistance. So now we can write this as the resistance, because the question is resistance, so we can write this k 1 by k, so that it will go up. So the here resistance will be 1 by K, but the resistance per unit area. So what will be the answer? Per unit area. So your resistance per unit area will be 1 by K per unit area. Yeah. So C answer will be the right one. Sorry. Yeah, C answer will be the right one. I gave the more wrong explanation here. Okay, now we are moving to the next part that is more important for us to understand the overall. The one is overall mass transfer coefficient, and another one is individual mass transfer coefficient. So here, if we have the small k, then it means we are talking about individual mass transfer coefficient. And if we do have capital, then it means we are talking about the overall, and overall will have both air, due to air, due to liquid, or due to air, due to solid. So just like that, we talked about the series resistance, right? So we have to do the summation in the series or in the parallel way. Okay. Now just read the question very careful, that if we have pure volatile liquid A evaporate into air. Okay. So let me give you examples. So let's say we have water and we do not have anything in it. This water will itself evaporate. This means your liquid, your A is nothing but A is water, and you have nothing uh, except this water. Okay, so you have pure volatile liquid A that will evaporate into air. Now you need to tell correct gas side flux. So you need to tell the gas side flux. This one. So here, what flux I will have? So the important thing that we need to consider is we have um, we have four things, right? You gave me B answer. Yeah, B answer will be the right one. But how this is, let me tell you. So this is something that if my water will evaporate and will go to the air, okay, it means, and here I have air, and I'm assuming is that in air I do not have water vapor, because water vapor is coming from the liquid only, pure liquid. So it means this layer will have more concentration of A as comparison to the concentration of A that we have in air. Is it? So it means uh, if it has more, and if I'm calculating the difference in the concentration, dc, if I'm calculating, so this dc should be your A in your interface. I'm writing here interface minus Ca in the air, and in air I have zero concentration. So I write like this? So if I'm writing this like this, then the another thing that I can do is I can change this one. The first thing that you just keep in mind, then in the air your film will have more concentration of water vapor as comparison to your air itself, because it is moving through this film only. Okay, so this is the one equation that I can write, that cia, I is interface. So the concentration of A in the interface minus concentration of A that I have in the air, that will give me the difference in the concentration. Okay, the second thing what I can say is that Here also I have interface in the water side, right? In the water side I also have some concentration, and we always assuming that uh, these two interfaces are always in equilibrium, are in equilibrium. So in equilibrium, it means, what I can say is that I have C in the liquid side, I, and this is in equilibrium with Ca2 I. So A, sorry, 1. Okay, if these are in equilibrium, then in place of this I, we are, as we are saying, it is the star. So star is equilibrium, right? So what we can do is we can change it to the equilibrium, because this interface is in the equilibrium with the opposite interface, and that's how this will come. So this is the difference in your concentration, and this is your mass transfer coefficient that that have your resistance term, right? Resistance due to resistance, and that also have diffusivity and diffusion coefficient, and a lot. There is a lot of things that we have in the small ka1, but the thing is, B answer is the right one. And how we can do this, I just explained this. Okay. Or the another way that we can explain is that, so this is the one way. The second way that we can explain is that uh, your gas side concentration of A is zero, mostly zero, right? It is mostly zero. What we are assuming is that because water is evaporating and going to the air, with the time there will be the equilibrium condition between these two phases also. So the maximum concentration that air can have is the saturation, right? And this saturation is by this. So the first thing that I told you is applicable even when we do not have the pure substance. But if we have pure substance, it means that we can calculate the imaginary with the imagination we can calculate the equilibrium condition. So this is something, this is your water, and water will go to the air, will go to the air. So the maximum concentration of your water in the air will be when your air will be in equilibrium with the water, and that's how this will be your maximum. So this will be your maximum, and minus whatever concentration we have. So this is initially it is 0. Okay, so this is how we can calculate. This is the when we have the pure substance. And the second that I explained with that interface condition and then equilibrium of these two condition with each other, so that is the default. So whenever we do not have any pure substance and all, then we can go with that original formula. But for now, this one is applicable for whenever we have pure one. Okay, again we have pure DNAPL. What is DNAPL? DNPLA dissolve into water the correct water side flux. Again, you can consider the equilibrium condition, right? So what is this DNAPL? Can you tell me the full form of this? Dense, non-aqueous, non-aqueous. What type of liquid? P means, P means what? Phase liquids, right? So yeah, non-aqueous, dense non-aqueous phase liquid. So this is something that, for example, uh, there is something that if you have a ship and that ship is uh, draining something in the ocean or in the sea, okay, and that will go to the bottom in the water, okay, and this is pure. So this is, let's say, A, and this A will move to the water. This A will move to the water. Now correct water side flux is, um why not A? Why you gave the B answer? First thing is, if it is a water side, then this will not be the right answer because this is A1, right? So the answer will be from A, B, C. Then we can't have the difference in different phase. The phase should be same. So this is again not the right answer. This is not the right answer. The answer can be from A and B only. So which one is the right answer? Equilibrium condition will have more concentration, or non-equilibrium condition, then you can have the difference in the concentration. What will be at the first and what will be at the second? If you have pure one, A or B. So that's why I gave you. So this is something, again, let me explain you. So this is something that you have this pure one A, and that I have at the bottom. Okay, then the maximum concentration of this A in the liquid can be when water is in equilibrium with this pure A. Okay, so the maximum concentration of A in water can be when water is in equilibrium. So this is your maximum concentration of A that can I have in the water. Okay, so the maximum, and what we do is, we subtract always concentration high minus low. So if it is, if there is a solubility or if there is a saturation, the highest concentration will be at saturation, at equilibrium, at the solubility level. So it means this is your high condition. This is your highest condition. And then what concentration we have right now of A in the water, if we are subtracting it, then we are having the difference in the concentration. Is it? I think that makes sense, right? Because always the concentration should be high minus low, and the high concentration of this A in the water can be only when A is completely or saturated in liquid, right? And what, when this can be happen, when there is a equilibrium condition. So it means this is giving me the highest concentration of A in water, right? And initially we may have zero concentration of your pure A in water, then this is zero, or you can say anything. So this is how, please keep in mind, if we have concentration, then it always be high minus low. Then you have to see at what direction we should go. Okay, and that's how A is the right one, not B. Okay, for evaporation of pure water in air, saying interfacial air concentration equals saturation concentration. Again, uh, okay, so just let me tell you, uh, the one example that we can have is, we have here liquid and here we have gas, and let's say here we have some a pollutant, or we can call it as the solute. If this solute is moving in this direction and in this direction, okay, this is this is a more complex situation as comparison to, we have liquid and we have gas, and that liquid itself is going to the gaseous phase, or that gaseous phase itself is going to the liquid phase. So here in this condition we can simplify a few things. Okay, simplification is that, if the concentration of this liquid in the gas will be highest when there is the equilibrium condition, but here the conditions are more complex and more challenging. Okay, so yeah, so that's why whenever we have such pure things, if you see pure substance, pure air, then it means equilibrium condition can simplify your equations. Okay, so yeah, so if you have pure water into air, then this will be equal to the saturation concentration. Means what? Bulk air is saturated. Air at the interface is equilibrium with liquid water. Liquid concentration equal air concentration numerically. No evaporation occur. So this is that air at the interface is in equilibrium with the liquid water. Is it? So that's how we can, we are making two, within the same phase we can make the differences, that can make us the possible. Yeah. Why are individual mass transfer coefficient difficult to measure directly in two phase system? Diffusivity is always unknown. Bulk concentration cannot be measured. Interfacial concentration are difficult to measure. Flow velocity cannot be measured. Why it is always difficult to calculate the individual mass transfer coefficients small k2 and k1? We can't calculate it directly, never. We have to have some assumptions, and we have to move around so that we can calculate this k2 and k1, because these are dependent on the interfacial concentration, and interfacial concentration we can't measure. So that's why the answer will be C. Okay. Overall coefficient are useful because they eliminate the need for equilibrium relation, eliminate the need for interfacial concentration measurement, make diffusion coefficient unnecessary, only apply to pure liquids. It might be little, yeah, it is easier, I think. Yeah. So overall coefficient, because it is, we will see how we can remove this interfacial concentration measurement and how we can play with different terms. So yeah, B answer is the right one. Okay, so now we will learn. We will learn the derivatives and at length how this interface is playing role, the thin film and the thickness and all. Because I will give you the full derivation. So for a dilute solute, okay, so now we are not talking about the pure thing. Now we are talking about the solute. If solute is transferring from water to air, then overall air side coefficient is related by If it is the overall, then we are talking about capital K. And if it is the air side means A1. A1. And because we already have learned that overall coefficient, the resistance is in series. So we have 1 by something, right? Then this is actually the formula that you should mug up, you should learn, because most of the question you can solve using this formula. And I will tell you the derivation of this also. Okay, so if it is air side, water to air, then yeah, C answer is the right one. But how this C answer is the right one? How you get? The first thing that very important to get to know is that if this is the air side, then air side will be directly proportional to the Henry constant. If it is the water side, then this will be the inverse. There is an inverse relation with the Henry constant. So it means this is the direct. Okay, so C answer is the right one. First is this one is your air side coefficient, individual coefficient, and this is your water side coefficient, Ka2, and this is your Henry constant. Now we will learn from where this came from. Okay. Okay. Now I'm taking because this one is water to air. Just keep in mind that this is water to air. So again, I'm drawing the same thing. You have here water, and here you have air, and here we have film. Okay, and so this is, here you have rho A2I, and in that particular place we have rho A1I. Here we have rho A2, and here we have rho A1. Is it clear? For the I means interface. At the interface, we have some concentration of A, and if we are going away from the interface, then we have the concentration of A in air and in water as rho A1 and rho A2. Okay, now we are going to the flux. Okay, flux in the air side film. So if it is moving from water to air, so this is the direction of flow, right? This is your direction of flow. It means if we are comparing these two things, if we are comparing these two things, the concentration at your interface and concentration at your air, in your air, it means this will be more because this is moving from water to air. Is it? At interface, in the air side, the concentration will be high, so this is high and this is low. Okay, because first your interface will come and then you will have the air. Okay, so I think there is a no problem with this equation. This is your mass transfer coefficient at the air side, A1, and high concentration will be at your interface. So that's why this is rho I A1 minus rho A1. There is no problem. This, then we are rearranging these things and we are getting this one. Okay, but as I told you, this one is very difficult. The concentration at your interface, we can't measure it. Okay, though, so we have to do something. We have to do something so that we can have some value of this with some simplification. Okay, because we can't measure it. Okay, this is your first equation. Now, if we are going to the water side, then what I know is that this is moving from this way to this way, right? From water to the interface of the water. It means your this part, your rho A2 will be more than rho A2I, is it? So this is your larger. So this is your high and this is your low, and that's how we are maintaining the concentration difference. Okay, and again we are having the equation 2. Now what we will do is that we have this term also, right? And we have this term also. So we have interface concentration in the gaseous side or in the water side. We need to change this into something, so we have to change this. Okay, and how we will do this? Yeah, so how we can do this? We can use the Henry law. So Henry law, what Henry law is saying, that the air, the concentration of A in the air is directly proportional to the concentration of A in liquid, and if we are equaling it, then there is the Henry constant. Okay, then but this is in the equilibrium condition. Again, I'm drawing the same thing, and here we have interface. And the second simplification what we are having is that these two interface are in equilibrium, here we had the concentration rho I A2, and here I have rho I A1. These two phases are in equilibrium. Okay, and if they are in equilibrium, then we can apply this Henry constant in this interface, right? So this is how we are applying this. So the concentration of A in gas side but in the interface will be equal to Henry constant rho I A2. Okay, now the things will be very simpler. Now what we are doing is, we had this one, right? We had this equation. So what we are doing is we are multiplying this equation with the H. So we are multiplying this equation. We already have also the lower one, sorry, uh, these equations here we have. So we are multiplying the water film side equation with the H. Okay, and then what we will have is, we will have one term this one and one term this one, H multiplied by rho I A2, and this one. So here we already have few things that we have calculated, right? So this H rho A2 will be equal to this rho star A1 that we have calculated from here. So let's say this is 3 and this is 4. So this came from 3. This was your equation 2, right? And yeah, so in equation 2 we have two component, and first component we are getting from equation 3 and second component we are getting from equation 4. So now we are adding everything, then what we are getting is this one. Then yeah, so we have air side driving forces. Air side we have, if we have concentration in equilibrium, that will always have higher and this will have lower. Then what we are doing is we are just adding and subtracting this one, and then we already have calculated these things. So from here we are getting the equation, and then we are cancelling the flux from both side, and yeah, this is over how we are getting it, right? So so what we are doing is we are substituting this item with some concentration, and then we are cancelling out the things, and then we are calculating here mass transfer coefficients and the resistance. Okay, and that's how without knowing the concentration of your interface, we are dealing with the coefficients, and that's the beauty of this formula. Okay. Now, if you have overall, you have to tell me overall water side coefficient. Water side coefficient is a little different from the previous one. What will be the formula for overall coefficient if we are calculating from water side? Water side means air to water. If we are having condition air to water, if we have a that is moving, then there will be some resistance, and there will be some coefficient. Then how we can calculate this? What is the formula for that? So as I told you, in air side coefficient, you had Henry in the numerator, right, at the top. But in water side, H will be at the denominator, with the denominator. So Ka2, here there will be Ka2, and for the A1, for the air, there will be the Henry constant with it, but at the bottom. Okay. We also have derivation for it, but I think that is kind of boring thing that can to make you understand, so I'm skipping it right now. But if you want it, just let me know. This is again the simple way. In previous one we multiplied with h, here we will divide with h, and most of the time the things will be same only. And yeah, so this is the crux that we are getting. So these this is for your water side coefficient, overall coefficient. This is your air side coefficient, and these are your flux at the water side and flux at your air side. Based on that, then I will give you some numerical that you can solve. Okay, so just keep in mind these equations. The same hydrodynamic condition, mass transfer coefficient for chemical B is estimated from A by this D is diffusion, diffusivity, D is diffusivity, and MW is your molecular weight. So, and we already have learned, right? This individual mass transfer coefficient A or 2 is very difficult to estimate. So we have to estimate this using some scaling factors. uh, Actually not the molecular weight. um, More than the molecular weight, diffusivity is more important. Diffusivity is more important than the molecular weight. So whenever we are scaling to calculate this mass transfer coefficient for any chemical from another chemical, then diffusivity is more important. Molecular weight is important, but yeah, diffusivity is more important because diffusivity itself is taking into consideration the molecular weight. This is B. This is something that k this is kb divided by db will be equal to um, ka divided by da, and then we have this n raised to power n, right? So this is something that you just need to learn, no more concept. But yeah, you can read more about this. But this is something that you just need to learn, is that diffusivity is more important for if we do have same hydrodynamic conditions. Then yeah, why is molecular weight usually not used directly to scale mass transfer coefficient? I already have given you why we are not considering the molecular weight. We are considering diffusivity to scale the mass transfer coefficient, right? Yeah, because it primarily depend on diffusivity only. Okay, if we have steady state in the diffusion film, means concentration is uniform everywhere. Flux changes with time. Concentration at each location does not change with time. Concentration profile must be zero. I think you must be confused with option A and option C. Concentration profile must be zero. No, this is not the case. Flux changes with time. In steady state, flux doesn't change with time. So this is also not the right answer. We have A and C, in which we can have one answer. Concentration is uniform everywhere, and concentration at each location does not change with time, which is more appropriate. So if it is in the diffusion film, then yeah, this one is more relevant and appropriate, that each location, it does not change with the time. Okay, so yeah, C answer is the right one. A concentration profile in a diffusion film is linear if diffusivity is constant and no reaction occurs, diffusivity is zero, convection dominates, flux is zero. So this is something like that. As I told you, if we have air and if we have water here, and these are our films, then it is something that this is coming like this. Then there may be something like this. There may be something like this, and then yeah. So there are always some concentration that we have. So if it is a linear, so something like that, is it possible to have linear first? And if it is a linear, then at what, in what condition it can be linear? Linear means there is no any resistance here. And it is near to impossible that we do not have any resistance. A little difficult, but I think this is the easier one also. So diffusivity is constant and there is no any reaction is occurring here. So if diffusivity is constant, then only this type of condition can be happen, but it is near to impossible that we do have the constant diffusivity. Okay, so this is kind of imagination question only. Okay. If we have well mixed lake that have no inflow and no outflow, pollutant is removed only by volatilization with first order behavior. If concentration half in time t 1 by 2, the rate constant is. I think this is a little different from what we are reading till now. This is related to the first order reaction. So, what is the first order reaction? Can you tell me the equation for first order reaction? The change in concentration with the time is directly proportional to the concentration itself, is it? This is your first order reaction. So this is something dc upon dt is equal to kc. So it is something that dc upon c is equal to k dt. And then what you have to do is, because the concentration half, so let's say you have initially concentration is equal to c node, but after half time the concentration will be c node by 2, right? And yeah, so this is how you just need to do little derivation and integration, and that's how you will get. So let me show you what you will get. Yeah, so this is your first order react equation, right? C, the concentration left is equal to initial concentration E minus, this is your constant and this is your time. So C by C naught, and we talked about this, that this has been halved. So this 1 by 2 is equal to 1 by 2 is equal to E minus KT. And here, because we already have halved, so this will be 1 by 2, and now we can calculate this k. So this is ln 2 by, so, and if we are going more further, then this is something 0.693 divided by half time. This is very important equation actually. Based on that you can tell uh, when your population will be double, after how many years your population will be doubled, because decay and exponentially increment. So based on such kind of equations we can calculate, even your interest you can calculate at after how much time your amount will be doubled with the interest. So this is how you can calculate using first order reaction. Okay, a lake has volume 1000 meter cube, area is 100 meter square, pollutant half life is 1000 second, assuming volatilization only. So can you calculate k? Everything is given, you just need to calculate k. How you will calculate? You just need to calculate this one. How you will calculate? Let me give you, yeah. So here, if we are rearranging the things, then what we will get is, um, let me tell you here also. So again, so we have dc upon dt and we have c, and then we are having the half life, then it means we have to divide, and then we will have 1 by 2, right? So here if we will have 1 by 2, then k will be equal to v divided by a, time half time, half lifetime, and logarithm, so natural log of 2. And yeah, this is how we can calculate the k. Okay, so if we are moving from water to air, if Henry constant is given as the ratio of concentration, then which one will be the right one? The first thing, we are moving from water to air, right? So this one and this one is the right one, so this is not the right one, this is not the right one, because we are moving from water to air, right? So now which one will be the right one? So what we have learned is the concentration in air will be proportional to the concentration that we have in the liquid, and if we are equaling it, then we are having the Henry constant. So what we have to do is, again, if we have pure substance, then the highest concentration will be in saturation, and then this Henry constant will be only applied in the equilibrium condition. So this Ca1 will be in equilibrium, that will be equal to Henry constant multiplied by the concentration of A in liquid. This we have learned in a derivation part also. For volatilization from water to air, a very small Henry constant H indicates. If we have Henry constant that is very low, what does it mean? Strong preference for the chemical for the air phase, no interface mass transfer can occur, equal preference for water and air, strong preference for the chemical for the water phase. What is the role of Henry constant? What will happen if the Henry constant will be lower, and what will be the higher? The solubility of any A in air will be higher or lower if your Henry constant is high, and same like this one. Based on Henry constant, the solubility of A in air is determined. So it will be strong preference, or it will be low preference in air. If we have more, the value of Henry constant is more, it means your solubility in air will be more. Is it? Is it? Yeah. So this is something, Henry constant. If the Henry constant value is high, is it means your any contaminant A will be soluble more in air, right? If H is low, it means your A will soluble less in air, but will give the preference to the water for the solubility. So that's why D answer is the right one. This type of question we already have done, so I'm skipping this one. Yeah, this one is more important. For dissolution of pure compound A, again, see, we have pure compound A in water. So this is something that we have this pure substance A, and we have water here. And if this pure substance A is going to the water, what driving force give positive flux into water? So again, very simple. So because we have pure thing, right? If we have pure thing, then we can remove this I things, interface things, because we can directly talk about the equilibrium, right? So the concentration in equilibrium will be higher or lower. B is bulk. Again, simple. So the thing is, we have A, right? We have concentration of A. So it is something that we have sugar, right? And we are adding sugar into the water. Okay, so it means if we are moving it and this sugar will go to the water, the highest concentration of sugar in the water will be only when there will be solubility or there will be saturation. It means equilibrium. So equilibrium will give me the highest concentration. So this is my highest concentration that I can get in the water of A, minus right now whatever concentration I have in the bulk of A in water. And this is your low, low to high. We are maintaining it, right? So that's how B answer is the right one. Yeah. We already have talked about this, so we are gonna skip this. Yeah, very important. Uh, Mass transfer coefficient depend on molecular weight, hydrodynamics, and diffusivity. Which we already have talked about such type of question in previous one. Only temperature, only concentration. We talked about this, right? Mass transfer coefficient is more, we can do the scaling using diffusivity, right? And the condition was when we had the same hydrodynamics things. If hydrodynamic is also different, and then we have to consider into this two factor, hydrodynamics and diffusivity. And this is depend on this equation, but what it is, let me show you. So this is the first is the Sherwood number. And in Sherwood number, you can see this is the diffusivity. This is your mass transfer coefficient. So your mass transfer coefficient is dependent on your diffusivity, right? Then Re, that is the Reynolds number. Uh, Again, we have this one. This is giving you the hydrodynamic things. This is giving you the diffusivity. And this Schmidt number is also giving you the diffusivity. And so it means your mass transfer coefficient, the variable that we have in the Sherwood number, is depend on your three terms, and these three terms will give you some information about the hydrodynamics and the diffusivity. Okay, if your Ka1 is equal to 2 multiplied by 10 raised to power minus 5, your equilibrium, in equilibrium condition, the concentration of A in air is 300 mg per meter cube, and the bulk air concentration is 0. What is flux? Now we are making use of all our equations. So is it something that flux is equal to K, capital K, A1, A1 minus Ca1. This one is given 300. This one is also giving 2 into 10 raised to power minus 5. And this bulk air concentration is given 0. So can you calculate the flux, just the multiplication part? So this is how we can calculate, and what it will give is A, that is 0.006. Very simple. Uh, we just calculate this one question and then we will go. Again, we have pure liquid. In the pure liquid, you do not need to care about this I. You can deal with the constant equilibrium conditions only. So if you have pure liquid that have the saturated water vapor concentration in the air, that is 500 mg per meter cube. Bulk air also contain 100 mg per meter cube. If Kai is equal to 10 raised to power minus 3 meter per second, then flux is saturation means A1 minus A1 bulk. Yeah, yeah. So, and here we will have the Ka1. Yeah. So A1 is the right answer. Time is up actually, and I have few numerical question. At least I have 10 to 15 question that I need to solve, but it's all right. We can solve this in next week. So if you have any problem, you just let me know. Otherwise, you can leave. So again, we will meet on the next Tuesday. The last session will be only on 14 April, and before that I think 12th April also I have one more session, and one on 7th. So we will have three more sessions that are left. The one is on 7th, another is on 10th, and another is on 12th, something like that. I will let you know. But yeah, three sessions are left, and I think we will able to complete all the course. So thank you so much. If you have any problem, you just let me know. Otherwise, you can leave. Have a good dinner and good night.